Welcome to this explainer. Okay, today we're diving into something truly massive, the incredible scale of industrial heating. Have you ever stopped to wonder what actually drives the immense power behind manufacturing or even global power generation? Well, drawing on some really fantastic research by Deepak New, we're going to be looking at the industrial boiler. This thing is the absolute ultimate industrial workhorse. We're going to break down exactly how these incredible machines take raw fuel and transform it into the high-pressure energy that literally powers our modern world. Let's get into it.
So, here's our visual roadmap for today. We'll start with the combustion process, then check out the anatomy of a boiler, look at different boiler types, evaluate their efficiency, and finally, wrap up with boiler water treatment.
All right, part one, the combustion process, sparking the cycle. This right here is the very first stage of our journey, converting raw fuel into usable heat. When biomass fuel enters the furnace, the absolute first thing it does is lose its moisture at around 100 degrees Celsius. Once it's dried out, it continues to heat up and starts releasing these volatile gases. We're talking hydrocarbons, carbon monoxide, methane. Now, here is the crazy part that Deepak Nay's research points out. In this process, those volatile gases actually contribute about 70% of the total heating value of the biomass. No way, right? It's not just the solid mass burning. It's really the gas that brings the intense heat. And then finally, the remaining solid char oxidizes, leaving just the ash behind.
But, fire needs air, right? And a boiler desperately needs a way to exhaust the leftover products safely. So, there's a clear mechanical escalation for these draft systems. Step one is the natural draft. This relies purely on the chimney, where lighter, hot air just naturally rises. Simple enough. But industrial boilers, they need way more control. So, step two is induced draft, where a fan actively pulls gases out of the furnace, which creates a slight negative pressure. Step three is forced draft. That flips it by using a fan to actively push combustion air into the furnace. And finally, step four is the balanced draft. This is the most controlled environment, utilizing both forced fans to push air in and induced fans to pull gases out at the exact same time. Moving on to part two, the anatomy of a boiler, the industrial tea kettle.
So at its core, a boiler is essentially a giant, highly pressurized tea kettle. To make that heat transfer happen, it relies on three main systems. First up, in blue, the feed water system. This provides treated water to the boiler and automatically regulates it to meet the steam demand. Next, in red, we've got the steam system itself. This collects and controls the high-pressure steam we just produced and directs it right through piping to exactly where it's needed in the plant. And finally, you have the fuel system. That's what provides the raw energy to generate that necessary heat in the first place. It's just a continuous, dynamic loop transferring heat from the burning fuel directly into the water.
Okay, part three, different boiler types, fire versus water. As you can probably guess, not all boilers are built the same. The structural designs actually change quite a bit based on industrial demands. And the primary distinction here is fire tube versus water tube boilers. In a fire tube boiler, the hot gases of combustion literally pass through long steel tubes, and those tubes are completely surrounded by the water that's going to be boiled. This design is great because it has a lower initial cost and it's pretty easy to operate, but, it is generally limited to lower capacities and pressures. Now, the water tube boiler reverses this entirely. Here, the water passes through the tubes, and the hot combustion gases circulate on the outside. This switch allows for much higher pressure thresholds and massive steam capacities. It really is a complete physical reversal. In the top fire tube setup, the fire and hot gases are safely contained inside those central tubes, which then boils the vast pool of water around it. In the bottom water tube setup, it's the exact opposite. The water is intricately piped through a network of tubes, while the massive combustion chamber just fires all around them. It's a simple geometric flip, sure, but it completely changes the physics, the efficiencies, and the overall capabilities of the machine. All right, moving into part four, evaluating boiler efficiency, measuring the workhorse. Running these massive machines requires, massive amounts of fuel. And because performance naturally deteriorates over time, we really have to keep an eye on boiler efficiency. Now, that's defined as the percentage of heat input that is effectively utilized to generate steam. So the absolute crucial point here is figuring out exactly how much of that incredibly expensive fuel energy successfully transforms into useful steam, as opposed to, just escaping up the chimney or radiating out into the boiler room as totally wasted heat.
Engineers actually evaluate this in two different ways. The direct method is pretty straightforward. You just compare the steam energy output directly against the fuel energy input. Easy, right? But to find out exactly where you're losing efficiency, you really need the indirect method. Instead of just looking at the steam, this method starts with an ideal 100% efficiency and systematically subtracts all the various individual heat losses mathematically to find out what you actually have left.
To distill the complex math of that indirect method, let's break down the heat balance for a coal-fired boiler. Notice that the biggest thief of heat escaping the system is the dry flue gas. It takes 10.7% of our energy right out of the stack. Next is the loss due to hydrogen in the fuel turning into water vapor, stealing another 4.4%. When you add up all these tiny little losses, things like moisture, unburnt ash, surface radiation, and subtract them from 100, you are left with your true boiler efficiency. In this example, that's a highly realistic 80.7%. Identifying these specific losses is a real game changer because it allows engineers to target exact areas for improvement.
And finally, Part 5, boiler water treatment, the plant's arteries.
Look, you can have the most efficient combustion in the world, but without aggressive water treatment, you are straight up heading for catastrophic failure. Think of scale deposits like cholesterol in the arteries of the plant. Untreated water contains hardness salts that create this stubborn insulation inside the tubes, and because the heat can't properly transfer from the fire through the metal and into the water, the metal temperatures of the tubes start to rise uncontrollably. This is exactly why this matters so much to every plant operator. Just a surprisingly small deposit of scale can cause the metal to overheat, weaken, and ultimately result in a massive, dangerous tube blowout. Definitely not something you want.
Aside from scale, water also carries silent killers like dissolved oxygen and carbon dioxide, which severely corrode metal piping. Enter the DAC aerator. This is just a brilliant piece of mechanical engineering that completely solves this problem. By preheating the feed water, often using exhaust steam, the deaerator mechanically strips away these dissolved gases before they ever even enter the boiler. It physically vents the oxygen and carbon dioxide out, essentially purifying the plant's bloodstream, for lack of a better term, and ensuring the boiler's longevity and structural integrity. So from the roaring flames of the combustion chamber all the way to the meticulous purification of the feed water, the industrial boiler really is a true marvel of thermodynamics. But as we know, technology never stands still. As global industrial demands continue to grow, how will the next generation of boilers balance extreme pressure with ultimate efficiency? It's a huge challenge. Thank you so much for joining me on this explainer. Keep exploring the incredible machines that power our world, and I'll see you next time.